thing. So, Evans, yeah, thank you. Andrew.
Good morning, everyone. It's nice to be here. It's nice to see everyone here. So, as Andrew mentioned, I'm going to be talking about carbon capture and storage. And I want to start off by saying that there's going to be a report released today by the International Energy Authority, which is predictably saying that we need to be accelerating our moves towards net zero. However, the report is fairly pragmatic. It highlights some things that have happened well. So, for example, prior to the COVID pandemic, 1 in every 25 cars sold in the world was electric. Today, that number is standing at 1 in 5. But also the pragmatism indicates that that means that 4 in every 5 cars today is using petroleum products. So we still have a challenge to face in terms of accelerating the energy transition, not just in terms of moving on to new technologies like electric, not just in terms of, in our particular context, using the subsurface for geothermal, for hydrogen storage, for CCS, but also decarbonising whatever remaining oil and gas production is going to take place. So I'm going to be talking specifically about CO2 migration and dipping structures. Before I do that, I just want to mention the overall topic that my chair program is working on, and I want to highlight here the group of students that have been working. Some of them are registered at Heriot-Watt University, some of these are visiting students working alongside us on various topics associated with basically reservoir engineering, where fluid and fluid rock chemical reactions are important. So that's what we concentrate in the chair program, and we're using reactive transport modelling to achieve that. So 3 main activities for that: subsurface gas storage, be that CO2 or hydrogen storage, mineral scaling in wells, be they oil and gas production wells or be they geothermal wells, and geochemistry aspects of enhanced oil recovery. So looking at water composition as it's injected for perhaps WAG, perhaps CO2 WAG, and altered salinity systems, and what impact that the geochemical reactions in the reservoir have on that. And I've highlighted 4 of the students here, the little red boxes. I'm sorry, there's no access to a pointer at the moment, so you're going to have to bear with me either trying to point in all directions simultaneously, which probably won't work, or I'll try and describe what I'm seeing in the slides to you. Hopefully we'll get that problem sorted out later on this morning. So on the first 2, upper 2 are Ali and Patricia, and they are working on the reactions that take place in the reservoir between the injected fluids, be it water, perhaps low sulfate water, or CO2, and the fluids present in the reservoir, how the geochemical reactions then impact those fluids as they propagate through the reservoir and show up at the production wells. And the bottom 2, Mahdi on the left and Celia on the right, are looking at particularly at scale management. Mahdi is looking at near wellbore modelling of scale inhibitor treatments in carbonate formations, where there are coupled reactions between adsorption and precipitation in the scale inhibitor and the influence of the minerals and the water composition in the reservoir. And Celia is looking at the interactions between enhanced oil recovery polymers and polymers that are used for minimizing scale, inhibiting scale from forming. So they all have posters, and I encourage you to go and see those posters. But basically what we're doing is looking at trying to accelerate the energy transition by working on CO2 storage and also hydrogen storage. So, question for you. Plot here, what does that represent? Any suggestions? Could have been my dot, sorry? It could be well trajectories. It's not, but it could be. It could have been my 5-year-old daughter's, my daughter when she was, she's not 5 now any longer, unfortunately, but when she was 5, her scribblings. Discrete fracture networks. Any other suggestions? I'll tell you what it is. It's a map of pipelines in the southern North Sea. Do you get that, Susan? You do? Oh, well done, well done, well done. So the point about this is just to show the locations of existing gas and gas condensate fields and the pipelines that are connecting them in the North Sea, as things stand today. What are the plans for the future? Well, the yellow boxes that you can see, so there's one right at the top left there, identifies future licensed areas by the UK authorities for oil and gas extractions. There's still licenses being issued at the moment for that. The blue ones are the areas that have been licensed for CO2 storage. The pink ones, the kind of pinky purpley ones, if you can identify them, are the ones that will be coming up in the next round of licenses for CCS. There's a green one at the top, that's the Endurance project, so that's now with the Crown Estate going on to the next stages of the development of that project. So what I want to convey to you here is the degree of overlap that there is between the plans for carbon capture and storage in the southern North Sea, existing oil and gas, which you can see in the kind of red blobs there, and the infrastructure that's there, the pipelines and so on. So there's going to be interactions between these. We're going to be looking at CO2 injection in systems which are perhaps already depleted gas fields, so at lower pressure. So that raises challenges of hydrates and freezing, for example, due to phase changes. We're looking at interactions with ongoing oil and gas activities, so there may be pressure communication between CO2 projects, and this is becoming a major concern for the authorities in the UK. If you look on there's a number for block 47 close to the shore there. It's quite a long blue licensed area. Now the regulator is clearly thinking that there's going to be more than one potential CO2 injection project in that area. So we may also get interference between projects. You'll also notice it's quite close to shore. So that's part of the Bunter Formation. The licensed area is part of the Bunter Formation, which is dipping about 2 to 5 degrees and actually outcrops onshore just to the left of that picture, to the left of Hull. Potable water supplies may also be affected by these pressure changes. So the message here is that there may well be interferences. We can't just think of CO2 storage in isolation. It's going to be in a very busy space. So we need to understand how we're going to manage both CO2 and hydrogen storage, and that people are also looking at hydrogen storage in part of that area as well, how that's going to interact with whatever else is going on. And there may be pressure interferences. We imagine those might be negative. Actually, the regulator says nothing whatsoever about pressure interferences. So oil and gas extraction ignores pressure. Molecules crossing a boundary, that's an issue. Pressure transmission across boundaries, the regulations in the UK and most of the world, I suspect, say very little about that. That is something that's going to have to be addressed with CO2 storage. There may be synergistic benefits from pressure. We may be able to use the fact that we're adding energy to the system by injecting CO2 to help any remaining oil or gas production and perhaps replacing water injection with the energy supplied with the pressure supplied by the CO2 injection. We also need to think about plume migration, these CO2 plumes perhaps interfering with other activities going on. Okay, so what's our approach? Our approach is we're working in a busy hydrocarbon basin. There's already a lot of knowledge. There's obviously infrastructure. There's also a lot of knowledge present there, so we can use that. The data is telling a story. We need to listen to what that story is. And then to develop models to try and improve our understanding of the processes and to actually model real systems. So one project which is being carried out by a student from Chieti in Italy who's on loan to us for a 6-month transfer. No cost transfer, I'd have to say, which is good news. So we welcome no cost transfers. So he's looking at building a basin scale model, so maybe something that's 80 to 100 kilometers by maybe 40 to 60 kilometers in extent, using data from the literature, from the regulators, and also from industry that's been supplied. And he's going to be looking, so you can see that the map of it there. There are various structures in there. There's some gas fields. There's some geological complexity that has to be addressed in that. And his main interest is actually looking at CO2 migration between sites. But we're also going to use this model for looking at pressure interferences. So he's building up data from seismic and so on, and helping to populate this area, and then trying to identify potential pathways for CO2 migration. Actually, the concept that he and his supervision team have back in Italy is actually using multiple structures. So a deliberate fill to spill. I have my suspicions about this, but it's an interesting concept. I suspect that the regulator may struggle with this one a little bit, but actually filling a structure and then using that same injection well to fill the next structure beyond the spill point. But anyway, whatever, we need to have a better understanding of what happens when CO2 moves beyond a spill point, and indeed, what is the impact of the height of a spill point. If we change the spill point depth by 10 meters or 5 meters, does that mean the CO2 is actually going to spill out somewhere else first, and so on? What's the impact of heterogeneity in the system? So we need high-resolution models in the vertical direction to be able to resolve these, and that's going to prove a challenge. For the pressure interference, we probably don't need to worry so much about resolution. We'll be able to do a basic material balance calculation for that. While we're looking at the data, we've drawn in all the salinity data from the fields that we can access in this area to try and identify, so you won't be able to see, but in those grey boxes there are salinity numbers for various fields in the system. And the question there is, can we see any evidence of connectivity, or in fact of systems being disconnected, so they've got very differing salinities, that suggests they're not in communication. That's useful data for us in identifying potential interactions between different systems. And while we're talking about salinity, there's a question of halite precipitation. And I'm going to guess Rick might say something about halite. He's going to be talking about Aquastor later on, and I know halite precipitation has been observed by a video camera tool in the Aquastor project previously. So the salinity of the Aquastor is about 330,000 milligrams per litre. Got a range of a dozen different systems into which CO2 has been stored across the world, ranging down to Teapot Dome, which is not quite drinking water quality, but almost. In each of these systems, if you inject dry CO2, there will be some precipitation. The question is how much. And so we go down that list. I've identified number 6, Snovit, at 160,000 TDS, and they have evidence of halite precipitation. They had evidence of halite precipitation in their initial injection, which they had to treat with wash water treatment. So we know that at least down to about 160,000 TDS, halite may be an issue that would affect injectivity. But how does this change across the world and across the piece? And then not just halite. So in Aquastor, you can see that 61% of the deposit is halite. The rest will be other minerals. Now, in Aquastor case, I think it's calcium chloride that's the other main component. But down at the bottom, you'll see in the green box, so we've got a field, the Forbes field, which is in the Bunter in the southern North Sea. Again, a similar overall salinity to Aquastor, but you can see that about 3 milligrams per litre, so that's about 3 grams per litre, so that's about 1% of the deposit will actually be a mixture of calcium sulfate and calcium carbonate. Now, these are insoluble, so doing a wash water treatment won't remove those. So there's a question, what will be the impact of other minerals in this process? And we've done some modelling of the halite precipitation. So as I mentioned, halite's been observed in Aquastor and Snovit, excuse me. So doing some simple radial near wellbore models to understand the process of halite deposition. People performed experiments trying to get halite deposition and not actually seen particularly strong evidence of loss of permeability as a consequence. And the reason is they're probably doing the experiments wrong. And the modelling is identifying that the halite deposition is a consequence of a balance between viscous and capillary forces, so the CO2 flux into a zone being balanced by capillary imbibition, counter-imbibition, delivering water into that zone and an ongoing precipitation. If you just take a salty brine, precipitate out the salt from that brine in situ, you'll get a certain loss of porosity and permeability. But actually the evidence is suggesting that we're having to have multiple pore volumes depositing in an area. And it's this balance between viscous and capillary forces that can deliver that. Actually, there's a couple of photos there stolen from the Aquastor project showing the evidence of the halite precipitation downhole. So another issue is pressure interference between different systems. I'm going to talk a little bit about pressure interference and then about finish off with CO2 migration. So what we have here is a picture of, we're going to look at a particular system in the central North Sea actually. It's the Captain system. And I've drawn a red line that runs through various fields and two projected CO2 injection sites, site A on the right-hand side of that line and site B on the left-hand side. And the question being addressed here is, if we do CO2 injection into site A, what will be the pressure impact on the rest of that that system? Particularly, there's a couple of gas fields, and now depleted gas fields, Cromarty and Atlantic, midway between site A and site B. And what would be the impact on CO2 injection in site B if we first started doing CO2 injection in site A? Would we actually poison it? So this plot here is taking that little red line, that red line that we had zigzagging across the system. If you imagine taking either end in your left hand and your right hand and stretching it, you have approximately 90-kilometer long line there. And on the vertical axis here, we've got the pressure in the system. Now, the dotted line is the initial pressure. That's actually at hydrostatic head. So the system is a dipping structure. So on the left-hand side of the graph, it's shallower, and on the right-hand side, it's deeper. So the dotted line is the initial pressure. The red line is what happened after 9 years of gas production in this field at site A. It's called the Goldeneye field, operated by Shell. So this is actually, as far as the green line is actually history-matched data from a model. So the red line is the pressure profile. So you can see there's been approximately 10 megapascal pressure drop over the lifetime of this field. In the subsequent 5 years, there's a process called aquifer recharge. So water is coming back in and building the pressure back up again. And then we did an assumption of injecting something of the order of 6 million tons a year. And if we inject 6 million tons a year for 5 years, we get the purple line, which basically takes that zone back up to the original pressure. So we could store 30 million tons of CO2 in the system and take it back to its original pressure. We actually looked at what would happen if you kept on injecting at the same rate and the pressure going up in 5-yearly increments. In fact, the last one is 10-yearly increment. So that would correspond to 180 million tons injection on the orange line. Probably unlikely you'd ever go that far. The question then is, what is the impact of that pressure change on the neighbourhood? Any fields in the neighbourhood? Now, the first field that we come across is the Atlantic field. And so we can see that, in fact, there would be a potential increase in the pressure in the Atlantic field as a consequence of that, perhaps around 5 megapascals. At site B, which was the projected second storage site, it's probably less than 2 megapascals. So the loss of CO2 injection capacity in site B is relatively minor. There is some interference, but it's relatively minor. Okay, the second thing I wanted to talk about was plume migration. This is really the main thing. With this, I'll finish off the presentation. So plume migration has some benefits. The more the plume migrates, the greater the contact surface area between the supercritical CO2 and so we're looking at aquifer systems at the brine, and therefore the greater the amount of dissolution that will take place. That's good news. Also, as I mentioned before, there's this concept of fill to spill, of actually using multiple structures with injection in your original system as a cost-saving device. So if you can get the plume to migrate in the right direction to another store, there might be benefit in that. As I said, I think the jury's out a little bit on that, but it's an interesting concept. But there are also risks, of course. So the risk of CO2 migrating beyond some boundary that perhaps the storage complex boundary where we're going to be monitoring, so we're going to have to spend more money monitoring because the CO2 plume has migrated further. It might actually interfere with neighbouring oil and gas activities, or with another CO2 injection system, or with some other user of the subsurface, and it may in fact escape to surface. So this is a calculation that's performed as part of a project called the CASM project back in 2010, and what we're looking at there is actually the area just onshore, just south of Hull. So this is actually very relevant because this is part of that Bunter formation that I mentioned is connected to license area number 28, where there's a risk of CO2 migrating onshore. And in fact, on the left-hand model, this is moving towards where the system subcrops to the surface. So we certainly don't want to see CO2 emerging anywhere near there. So a question for you. Imagine a conceptual system. Actually, this is a model system. So imagine this modeled system on which we're injecting CO2 in the well, and there's a background drift flux And let's call that background drift flux, so the aquifer water is moving at a rate of 1 foot per year. So it's a relatively low background drift flux. And after a period of a couple of years of injection and then shut-in, and then we run the model forward, we observe the plume as you can see it there at the moment. You can see marked in red the extent of the plume. Question for you. If we were to reverse the flow of that background drift flux, if in fact the background drift flux wasn't from down dip to up dip as you can see it, but was from up dip to down dip, what do you think would be the impact on that plume? I'm out of time, so I can't take your answers to that question. Let me show you what the impact would be. The plume would actually migrate about twice the distance. Now, that is counterintuitive because we think viscous forces, water pushing the plume up. Viscous forces have got very little to do with what's happening here. It's actually the gravitational forces that are important. The background water is not saturated in CO2. It's coming into contact with the plume. If it's coming in contact with the tail end of the plume, it's causing dissolution at the tail end of the plume, which is shortening the plume. And that means if we shorten the plume, the height of the plume is also getting less. And as a consequence of that, rho GH is getting lower. With a downward flux of water, that dissolution is not taking place at the tail end of the plume. The water that's arriving at the tail end has already been in contact with CO2 and is saturated, is not dissolving any more CO2. And so the plume becomes elongated and actually travels faster. And so we have a plot like this one here, which over time is showing the velocity of the plume. This is the work that's been done by a student called Mauda Awaj, who's just finishing off just now. So initially, when we stop injecting, the plume detaches from the near wellbore area. The plume, as it detaches, the height difference between the leading tip and the trailing edge gets smaller and the plume decelerates. But then the plume stretches, and as it stretches, that H grows a little bit, and depending on the drift flux, we may actually see acceleration. So with that, I just want to conclude. First to say that we will not be able to treat CO2 and hydrogen injection in isolation in many scenarios. So we need to take context of the wider basin picture, and that will mean both pressure interferences and saturation interferences, the plume migrating out of the original store, for example. There may be advantages. So we've got data, we've got infrastructure we can use. We may be able to use the fact that some of these systems have been depleted to increase the storage capacity, but we'll need to watch out for certain flow assurance challenges. And then we'll really need to pay a lot of attention to plume migration beyond the boundary and the risk that may create, particularly with taking into account aquifer drift flux. So with that, I'd like to thank Energy Simulation for funding the chair and for their support for organising today, CMG for supplying the software that we've used in a lot of these calculations, and the sponsors and partners, and to you for listening. Thank you.
Questions on the mic on both sides there? Can we turn this one on, please? It's on now. It's on now. Okay, thank you. So again, state your name and affiliation. There's 2 microphones along the 2 aisles there. We have a question here online from Emily Serbies. Thank you for such a great presentation. I just had a quick question on pressure increase being a function of rock compressibility, which is in some cases can double the pressure increase. Could you please expand on what was the compressibility used on slide number 16?
1e to the -6 reciprocal PSI.
Okay, that was
the answer to that question.
Okay.
So it's so it's an interesting question about the impact of rock compressibility. Actually, something that was a surprise to me when I first learned this was that water is less compressible than rock. So hydrocarbons, so having the presence of hydrocarbons, another advantage of having hydrocarbons in the system is that it increases compressibility. So you can actually pump more CO2 in before the pressure rises. The next most important thing is the rock compressibility. And then the least important thing or the least impact is from the water compressibility.
Okay, thank you. There's another one here from Ali Papi. Hi, Eric. Nice talk. Thanks. Regarding the halide precipitation, I was wondering, is there any evidence if chemical reaction of CO2 with rock and fluids would affect the halide precipitation or vice versa? If salt precipitation would affect the chemical interaction of CO2 with rock/fluid? Thanks a lot.
So the key point here is that if the CO2 that's being injected is dry, it will have the capacity to evaporate water. And whenever it comes into contact with water, it will evaporate that water. It will quite quickly become saturated, and so this will be a near wellbore process, because once the CO2 has come into contact with water, as it's propagating, it's now saturated, and further dissolution, evaporation will not take place. But yes, dry CO2 will always evaporate water. It's inescapable that it will evaporate water. The question really is how much of the residual salt how much residual salt will precipitate.
Okay. No one in the audience here yet. Another question online is from Mohammed Usman. CO2 density change due to mixing with the reservoir fluids, says methane. Will this impact the plume migration?
Enormously. It's a really good question. So methane is less viscous than CO2, and methane is less dense than CO2. So we've actually done some calculations, and we've identified that the CO2 plume would reach a certain point in 1,000 years. If the CO2 plume were to migrate into a depleted gas field and mix with methane there, that plume, that mixture, would actually reach the boundary in just over 300 years, so about a third of the time, because the mixture is now, for three reasons actually. The mixture is now less dense, so the buoyancy force is greater. Secondly, the mixture is less viscous, and so the mobility is higher. And then thirdly, the CO2 is soluble in water, whereas the methane is not. So in fact, what happens is that plume migrates, it becomes purified, becomes purer and purer methane. So the CO2 injection may cause a spill of methane out of a system, and you could end up with actually eventually just a methane plume propagating through the system, leaving the CO2 dissolved behind it.
Okay, good. One question from the audience here.
I'm Tsuyoshi Matsura. I'm working at EBN. Very nice presentation, thank you. I had a question about the pressure increase in aquifers, yeah? Because because you talk about open aquifers, closed aquifers, but there's also this idea of kind of semi-closed aquifers where you can lose pressure through the seal if it's permeable enough. So what are your ideas on that?
My idea is not to worry so much about pressure loss through the seal, but to pay attention to pressure loss through the underburden rock. Because typically the underburden rock may have, it may not, but it may have a higher vertical permeability than the seal. A seal needs to be, by definition, sealing. The underburden, we don't particularly care. In fact, we don't pay much attention to the underburden. Certainly in hydrocarbon recovery, if you've got an oil field and you're doing water flooding, you're maintaining pressure, you're probably not really that conscious of what's happening in the underburden. We've done some calculations. I've got a student actually working on exactly this problem at the moment. So even a relatively modest vertical permeability in the underburden rock, because it's a very large surface area contact between that underburden and the target formation, can actually multiply up to quite a significant total transmissibility across the whole system. And so even a modest permeability in the underburden can help relieve pressure from the actual storage complex itself. I think also work needs to be looked at obviously the overburden, but you've got to be careful what you wish for there, obviously.
Okay, Eric, last question, I guess, from your former student, Hydra Rodriguez.
Oh, that's not a Hydra.
Great talk. She can hear you but cannot speak here. Eric, could you share the best practices to minimize halide precipitation during CO2 injection? Would periodically injecting water slugs to wash off the salt be enough?
So that's a great question, Hydra. You're forgiven for that. Very proud of Hydra. Hydra is now working in Norway with Equinor, on CO2 storage. She's done very well. So that's me trying to avoid the question. No, I'm not trying to avoid the question. The answer is, I think there are three things to consider. One is a wash water, a pre-flush, a lower salinity brine to displace the formation brine away from the near wellbore zone. However, I think that may have limited success because in the cases where we have halite as a risk, it's that capillary re-imbibition that's bringing the brine back into the dry out zone. And I think it would be very difficult to prevent that from happening. The second strategy is to use occasional wash water treatments, just pumping. It doesn't have to be completely fresh. So some people think, oh, you need to get fresh water out there. Seawater has a salinity 10 times lower than the salinity of Aquastar. So actually, seawater would dissolve 90% of the salt that you might get depositing in Aquastar compared to doing a freshwater treatment, and has other benefits. The third thing, and I think this is something they've identified from Aquastar, the problem arose in the wells when they shut in the well. So don't shut in the well. In fact, the higher, so actually the serious point here is the higher you inject, the further away that balance between viscous and capillary forces will occur further away from the wellbore. So maintaining a constant and high injection rate is actually going to be your best safeguard against halite precipitation.
Great.
Andrew, sorry, sorry, not an Aquastar thing. Actually, I probably can talk loud enough. But for people who follow Quest, so Quest has now gone through, I think, to 4 to 5 on the hot water flushes, and they're becoming less and less effective. And in fact, they are actually now incrementally losing injectivity. And it's likely because the precipitation is occurring farther and farther out in the reservoir, in which a flush is just, yeah, forget it, you're wasting your money. And the same, although we're at much, much smaller volumes in Aquastar, that's likely to be the same case in Aquastar, where the precipitation is going to happen farther out, where now you're going to have to find a way to deal with it naturally, because you're just not going to be able to treat it that far out. But that's just an operational thing at Quest, that it's just it's not working.
Sure.
Okay, once again, we thank Eric for his talk. Interesting, sharing the experience and whatnot.